Hello and welcome back to MathandBolt. In today's session, we continue our discussion on solving differential equations by using the method of variable separation. So here we have the first problem. So let us begin. So we will begin by dividing both sides of the equation with 1 plus x squared divided by y, and that should give us y times e raised to the power of y dy equals to x divided by 1 plus x squared times dx. So now this is in a variable separable form. That's because the coefficient of dx, which is x over 1 plus x squared, that's purely a function of x, and coefficient of dy, which is y times e raised to the power of y, so that is purely a function of y. So we can now integrate both sides. To find the integral on the left hand side, we need to integrate by parts, and this should give us y times e raised to the power of y minus e raised to the power of y plus some constant of integration, but we will not write it on the left hand side. That will be taken care of by one single constant of integration at the end. So this is equals to, so here what we do is we do a manipulation. So we're going to multiply by 2 and divide by 2 so that we can use the substitution method, and that should give us half natural log of 1 plus x squared plus the constant of integration c, and this is going to be the final solution to a given differential equation. Let's move on to the next problem. So here we have another differential equation. So let us begin by separating the differentials. First we will cross multiply. So we'll have cosine of y minus secant squared y times dy, and that will be equals to sine x plus natural log of x whole divided by x whole multiplied to dx. Now this is in the separable form, as we can see that the coefficient of dx is entirely a function of x, so is the coefficient of dy, which is purely a function of y. Now we will integrate both sides. So we have integration of cosine y dy, so that will be sine y minus we have integration of secant squared y with respect to y, so that will be tangent of y. That's equals to integration of sine x dx, so that will be negative cosine x plus integration. So we have integration of, let's do it separately. So we have integration of log of x divided by x dx. So here, if we assume that log of x is equals to t, differentiating both sides with respect to x gives us dx over x equals to dt. So that means we have t dt, which is equals to half t squared plus some constant of integration. So we get half t squared. So t here is log of x whole squared plus the constant of integration c. And this is the required solution to a given differential equation. Let's move on to the next problem. So here we have some differential equation given. So we begin by separating the differentials. So we were going to divide both sides with y squared plus 1 times x squared plus 1, and that will give us dx divided by x squared plus 1 equals to dy divided by y squared plus 1. So this is in the variable separable form. That's because the coefficient of dy is purely a function of y and coefficient of dx is a function of x. So we can now integrate both sides. So integration of dx over x squared plus 1, so that's pretty standard. So that will be the arctangent of x equals to arctangent of y plus the constant of integration c, and this is the required solution to our given differential equation. Let's move on to the next problem. Let's begin by separating the differentials. So we have dy equals to negative times x plus 1 times y plus 1 times dx. So what we want to do, we want to get rid of this y plus 1 from the right hand side, because we want the coefficient of dx to be entirely a function of x only. So we are going to divide both sides with y plus 1, and that's going to give us dy divided by y plus 1 equals to negative x plus 1 times dx. So this is in the separable form. That means now we can integrate both sides. The integration of dy over y plus 1, so that will be natural log of y plus 1. That's equals to negative integration of x dx, so that will be half x squared minus integration of dx, so that will be x plus the constant of integration c, and this is the required solution to our given differential equation. Let's move on to the next problem. So this given differential equation can be rewritten as dy over y squared plus 1 equals to x squared plus 1 times dx. So this is now in the separable form. That means we can integrate both sides. The integration of dy over y squared plus 1, so that's simply the arctangent or the tangent inverse of y equals to integration of x squared dx, so that will be 1/3 x cubed. So here we've used the power rule plus integration of dx, so that's simply x plus the constant of integration c, and this is the required solution to our given differential equation. Let's move on to the next problem. Let's solve this differential equation. So we can rewrite this differential equation as x minus 1 times dy equals to 2x cubed y dx. So we'll get rid of this x minus 1 from the left hand side and y from the right hand side. So that means we're going to divide both sides with y times x minus 1. So that will give us dy over y equals to 2 times x cubed divided by x minus 1 times dx. So we can see that this is in the separable form, and we can integrate both sides. So integration of dy over y, that's pretty simple and straightforward. So that will be natural log of y equals to 2 times. Now we need to integrate x cubed over x minus 1. So we'll use a trick here. So in the numerator, we have x cubed, so that can be written as x cubed minus 1 plus 1. So that means we now have 2 times integration of x cubed minus 1 over x minus 1 times dx plus 2 times integration dx over x minus 1. Now if we expand x minus 1 by using the identity that a cubed minus b cubed is equals to a minus b times a squared plus ab plus b squared, x cubed minus 1, so that will give us x minus 1 times x squared plus x plus 1. So this whole thing is divided by x minus 1. So we'll be left with only this particular expression, which is x squared plus x plus 1. So that means our integral now becomes, this will be equals to 2 times integral x squared plus x plus 1 dx plus 2 times integral dx over x minus 1. So finally we should get, so let me write down the final result. So that will be natural log of y equals to, so we have 2 times integration of x squared dx, so that will be 2/3 x cubed plus we have 2 times integration of x dx, so that's 2 times x squared over 2, so we have x squared plus 2 times integration of 1 dx, so that's 2x plus 2 times natural log of x minus 1 plus the constant of integration c, and this is going to be the required solution to a given differential equation. Let's move on to the next problem. So we have the following differential equation. So let's rewrite the terms on the right hand side as, so dy over dx equals to, we have e raised to the power of x plus y, so we can rewrite it as e raised to the power of x times e raised to the power of y plus e raised to the power of negative x times e raised to the power of y. We can take e raised to the power of y as the common factor from both the two terms. So that will be e raised to the power of y multiplied to e raised to the power of x plus e raised to the power of negative x. So this is dy over dx. Now we can multiply both sides with dx. So this will be this particular expression. Then we multiply both sides with e raised to the power of negative y. So we have e raised to the power of negative y times dy equals to e raised to the power of x plus e raised to the power of negative x dx. So this is in the separable form. So that means we can integrate both sides. So we have e raised to the power of negative y dy equals to integration of e raised to the power of x dx plus integration of e raised to the power of negative x dx. So on solving, we get negative e raised to the power of negative y equals to e raised to the power of x minus e raised to the power of negative x plus the constant of integration c prime, let's call it. So if we take this term to the right hand side, we have e raised to the power of x minus e raised to the power of negative x plus e raised to the power of negative y, and we bring c prime to the left hand side, or simply rewrite it as c, where we can say that negative c prime is equals to c, and this is going to be the final solution to our given differential equation. So let's move on to the next problem. So here we have the differential equation. So we begin by applying the identity. We know that cosine squared x minus sine squared x, so that can be replaced with cosine 2x. So that means our differential equation now becomes dy over dx. So that's equals to cosine 2x times cosine squared y, which is simply dy equals to cosine 2x times cosine squared y dx. Now we get rid of this cosine squared y, so we divide both sides with cosine squared y. So we have 1 over cosine squared y dy equals to cosine 2x dx. So 1 over cosine squared y, so that's simply secant squared y dy equals to cosine 2x dx. So this is in the separable form, so we can integrate both sides, and that should finally give us tangent of y equals to, so integration of cosine 2x, so that's sine 2x, and because we have 2x, so we need to multiply it by the factor half plus the constant of integration c, and this is the required solution to our given differential equation. Let's move on to the next problem. So we have this differential equation. Let's begin by simplifying the terms first. So we have xy plus x, so we can take x as the common factor. That will be multiplied to y plus 1 times dy equals to, so we have xy plus y, so we will take y as the common factor, leaving us with x plus 1 times dx. Now we will divide both sides with x times y. So we have y plus 1 divided by y dy, and that's equals to x plus 1 divided by x dx. So this is in the separable form, so that means we can integrate both sides, and that's simply integration dy plus integration dy over y equals to integration dx plus integration dx over x. So integration of y will be y plus integration of dy over y will be natural log of y equals to x plus natural log of x plus the constant of integration c, and this is the required solution to a given differential equation. Let's move on to the last and the final problem. So here we have the following differential equation. Alpha here is a constant, so let's begin by separating the differentials. So we have y times secant squared x equals to negative times y plus alpha times tangent of x times dy over dx. Now we'll multiply throughout with dx. So we have y times secant squared x times dx equals to negative y plus alpha times tangent of x times dy. Now we will divide with y so that this term is independent of y, and here we need to divide with tan x. So that means we're going to divide both sides with y times tangent of x. So that is secant squared x over tangent of x dx equals to negative times y plus alpha divided by y dy. So this is in the separable form. That's because the coefficient of dy, which is negative of y plus alpha divided by y, so that's purely a function of y, and coefficient of dx, which is secant squared x over tangent of x, so that's purely a function of x. So let's integrate both sides. Now this can be integrated by using the method of substitution, which will give us log of tangent of x equals to, and here we have negative, so let me write down the result straight away. So this will be negative y minus alpha times log of y plus the constant of integration c. So this is the required solution to the given differential equation. Thank you.